All right, with a slightly late start. Apologies for that. We can blame, well, I'd say British Rail. It's not British Rail, but, you know, trains. I was a bit late. But hey, look on the bright side. If you're here before me, it means you're not late. So look on the bright side. There's a lot of you tonight. This is great. It's fantastic. Welcome, everybody. Who's here for the first time tonight? Are you sure you're here for the first time? I'm sure I've seen you before. 1, 2, 3, 4.
Maybe at the pub.
Yeah, maybe. Okay, so you guys, welcome. Welcome to C++ London Uni. You have dropped in on lesson 5, session 5 of our module on C++ containers and algorithms. So at this point, you know, we've got a bit of C++ experience under our belts, and we've been looking at the containers and algorithms, so part of the C++ standard library. Been looking at that for a few weeks now. So if you're dropping in from, you know, completely fresh, then tonight might be a bit like, whoa, what's going on? Don't worry, don't panic. The slides for the previous sessions, except the last one that I forgot to do, but somebody reminded me, thank you. For the slides for the previous sessions are on our GitHub page, and also all the videos. So that's basically the slides with me talking over them. All of those are on YouTube. So if you're here tonight for the first time and you're thinking, this is crazy, I don't understand what's going on, don't worry. You can go back, you can have a look at all our past videos and catch us up. But also for those newcomers and for the people who've been here for a while but have not listened to me nagging them, we have a nice chat room on Slack. So Slack's a chat application. You can access it via the web, or you can download the client if you prefer. There's this CPP Lang channel for discussing all aspects of the C++ programming language. It's got a couple of thousand people on there, and in particular we've got our own room on there, /CPP London Uni. So if you go to that URL, cpplang.now.sh, it's got a little box in there. You just type your email address. It'll send you a link to come and join us, to join the CPP Lang channel, and then you can find our chat room in there. I'm just going to turn the lights down a little bit so the screen's a bit easier to see. Is that too much? Is that too dark?
That's too much.
That's too much. All right, we'll go up one.
It's fine.
How about that? Okay. Yeah, there are quite a few of you in tonight, so if at the back you can't hear me, like yell at me, wave your hand, throw something. Don't throw something because you'll probably hit someone in the front row instead, but, you know, let me know. Okay, so as I mentioned, this is week 5 of our tour of the part of the C++ standard library. And last week we were at the very nice offices of Bloomberg, for those who joined us. And they very kindly stepped in. And we were talking about iterator categories. So iterators are how the standard library containers and algorithms join up to one another. And iterators come in 5 flavors according to what they can do, basically. The higher categories have more operations available than the lower categories. And we also began with an overview of the standard containers. So I went through talking about vector and list. I think it's about where I got to last week. So on the menu for this week, I'm going to finish, well, pretty quickly actually, just go over talking about the remaining, not all of the containers that are available, but the more useful ones. And then we're going to talk briefly about algorithmic complexity and what that means and why it's important. It's not really essential to know to use the standard algorithms, but it's some useful background information. It's a tiny little bit mathematical, so if that's not your thing, then don't worry, you can switch off for about 10 minutes. We have no stream. Just give me a moment, sorry.
It's definitely streaming something. It's not. I got a notification saying there's live. No, it's live. There's just nothing on the screen. Oh, okay.
Okay, let me try that again. So this week we're going to finish talking about the last few containers. We're going to have some slides on algorithmic complexity. Again, not really essential, so if it's a little bit mathsy and it's a bit scary, don't worry too much. But for those of you into that kind of thing, might be interesting. And then finally we're going to have a sort of introduction to how the STL algorithms work. So that's on the menu for this week. We've got a bit less time than usual and quite a lot of material to get through, so I'm going to charge on and talk about the standard library containers. Can you just shrink the screen a bit? It's a little bit cut off. Oh, never mind. Doesn't matter. Yeah, it's all right. So the C++ standard library provides lots of container classes that you should use when writing your own programs. Data structures, which you should use. And we can divide them sort of broadly into 4 categories. So there are about a dozen, I think, in total, maybe a little more, about a dozen all told, of which sort of 3 or 4 get used very, very, very heavily. So, first of all, we have sequence containers. So these are the ones that you're perhaps most familiar with, where elements are stored in the order in which you add them to a container. So, if you think about how an array works, or arrays or lists in other languages, if you're familiar with those are what we would call sequence containers. The elements are stored in the order that you put them into the container. Then we have associative containers. These are containers which have their elements contain the elements in a sorted order. If the elements are sorted, then we can very quickly do fast lookup. We can find a particular element quickly. Then we have what C++ calls the unordered associative containers. These are what in other languages get called hash maps and hash sets. So these are very similar to the associative containers. The interface is very similar, but the implementation is a bit different. They use hash functions, and there are slightly different trade-offs according to which operations are faster and which are slower. And then finally we have these container adapters that are used for specific tasks. To be honest, these don't get used very much. Mostly sort of included them for completeness. But in all honesty, they don't see all that much use, as far as I'm aware. Certainly not in my code. So the standard containers are what are called class templates. So template in C++ is like a blueprint for how to produce something. So when we have a vector is a class template. When you write a vector, you put those angle brackets after it, and you say what type it's going to be a vector of. And that produces what we call a specialization of that template. It produces a version of vector purely for holding ints, or purely for holding floats, or purely for holding strings. And it means that the full weight of all the compiler's optimizations can be directed at purely a vector of ints or purely a vector of floats. Right? So it looks superficially similar to the way generics work in languages like Java and C#. It's actually quite different. So quite a lot more powerful, in fact. And it means that, for example, a vector of ints is not the same type as a vector of doubles. These are distinct types. A list of strings is not the same type as a list of bools. These things are what we call template specializations. So for the standard library containers, they're class templates. You have to tell them what sort of element you want to put inside them. And some of the containers, they have extra parameters which you can use to specialize the behavior. You don't really have to worry too much about that unless you're doing pretty advanced stuff. And in particular, I mention it because if you look in the debugger or you get some error messages, you might see references to something called an allocator. And that's a way to specialize how the container allocates memory. So behind the scenes, the container will go away and ask for some memory in order to store the elements. And this allocator template parameter lets you customize how exactly that works. 99.9% of the time, you don't ever have to worry about this allocator parameter, right? It's an optimization thing. If you're needing to get the absolute last 1% of performance, then you'd worry about the allocators. But I don't worry about them generally, and you don't need to either. But you might see it come up in either error messages, or if you're looking in the debugger, you might see a reference to the allocator. So that's what it is. Oops. Oh, we've got 2 bullet points for the price of 1. So the standard library containers are designed to have a broadly consistent API, broadly consistent interface in terms of the member functions that you call on these classes in order to do things with them. So for example, for a sequence container, to add something to the back of a sequence container, we call pushback. To remove an element from the back of a sequence container, we call pop back. To insert a value, we call the insert member function. And in particular, very importantly, all the containers have begin and end member functions, which return iterators. So this iterator thing that I've been going on and on about for the last few weeks, we call begin, it gives us an iterator to the start of a container. Call end, it gives us an iterator to one past the end of a container, and then we can pass the things that begin and end give us, we can pass those to the algorithms to do useful things with the elements of our container.
Are those the only iterators that you can use for these containers?
In general, yes. Yeah. However, we also have these versions called cbegin and cend, which return const iterators. So if you remember from last week, I think I mentioned them the week before as well, or the session before, we have iterators and we have general iterators, mutable iterators as we call them, will let you modify the elements via that iterator. But some iterators only provide read-only access to the elements. And we call those const iterators. So if you call begin and end on a read-only container, you're going to get a read-only iterator. But if you've got a mutable container, but you only need a read-only iterator, you can call cbegin and cend. It's a sort of safety thing. So if you can see that at the back, this URL on CPP reference has all the gory details about all the member functions for all the containers. In fact, the bottom of this page is a huge table that tells you exactly which member functions, which operations are available on which containers. So CPP reference, for those who haven't found it, is like sort of the Bible for C++ programmers. It's very, very kind of in-depth. But it's in some ways like reading a technical manual, right? Like it's a bit sort of dry, but the information on there is 100% correct, even if it's not always easy to follow. So I went over these last week, so I'll just do it very, very quickly again today. Again, if you wanted to go into these in a bit more depth, then the video from last week is available on YouTube. But sequence containers, we've got standard array, is a fixed size array of n elements. Right, so unlike a vector, which is a dynamically sized array, vector we can add things and remove things, we can change the size. An array just has a fixed size. That size is fixed when you create the array. You can never add anything to it, you can never remove anything from it. You can modify the elements that are inside it, but you can't shrink it or grow it. A vector, on the other hand, you can shrink it, you can grow it. You can add lots of things to it and then delete them again. All those nice things. A standard list. Yes, sorry.
Last week I came about a strange behavior of arrays where I was deleting an element somewhere in the middle of the sequence and then copying always the following element into the previous position, which resulted when it reached the end of the array that the final position was actually copied with an empty element and then removed from the array, so the size shrank actually in one position.
It definitely didn't, not for a standard array. So what you might have is sort of a moved from object at the end, or you might have a default constructed element at the end, but for an array there definitely will be an element there. Right? It just might be sort of default constructed, so it's empty, but it's still there. Whereas for a vector, the actual storage size changes. Right? When you delete things, or when you erase things from a vector, the actual physical storage changes. Well, actually it doesn't when you erase things, but conceptually you can think of it that it does. So array and vector, a particular vector is what you should be using most of the time. We also have standard list, which is a doubly linked list. So last week I went over a bit exactly what a linked list is and the difference between a vector, an array type, and a linked list. So if you want to know all about postmen delivering letters, go and watch the video from last week. There's also standard forward list, which is a singly linked list. So with a doubly linked list, we can move forward or backwards. A forward list, we can only move forwards. Forward list was added in C++ 11. I'm not really sure why, because I don't personally find it very useful, but there we are.
Forward list?
Yeah.
Well, it takes up less space. Yeah, point backwards.
Yeah. And then finally we have this thing called a deck. It's a double-ended queue, which is sort of a bit like a vector, but with some slightly different properties. And also worth mentioning, it's not technically part of the sequence containers like bit of the library, but it behaves a lot like one, is standard string. So standard string, yeah.
How about map?
That's not a sequence container. So standard string, you can think of it basically as like a vector that's specially for storing characters in it. Yeah.
Do we have sets as well?
Beg your pardon?
Do we have sets?
Sets. Oh, right. Yes. These are only the sequence containers. We'll get on to maps and sets in just a moment. Sorry. Really misheard that. So string is pretty much like a vector, but especially for storing characters, and it's got some extra member functions on there that are useful when we're dealing with arrays of characters. So again, I'm just going to run through these very quickly because I did go through them last week. But standard vector, if you're familiar with arrays or array lists, as they call them in some languages, pretty much every programming language has some notion of something like vector. Vector, unfortunately, is slightly ill-named because it's absolutely nothing to do with mathematical vectors. So if you know about maths and you know about vector spaces and things like that, that's not this. I'm not quite sure why they decided to call it a vector, but that's the way it is. That's the name we've had for 25 years, so that's what's stuck. Yeah. So the properties of a vector. Element access is constant time. We can access any element in the same amount of time, no matter how big the vector is. If we've got 10 million things in our vector, then doing vector square bracket 0 takes exactly the same amount of time as doing square brackets 10 as doing square brackets 5 million. Right? Element access is constant time. It's not related to how many elements are in the vector. If you don't know what constant time means, well, hang on, because we're going to talk about algorithmic complexity in a moment.
Question. What are the costs of operation on vector?
Well, that's what I'm going over now briefly. But if you want a really full in-depth treatment, have a look at CPP reference, because it goes into great detail about exactly the complexity of every single member function. So adding elements to the end of a vector is what's called amortized constant time. That basically means, like, if you do it enough, it looks like constant time. Sort of vaguely, roughly. Right, so when we add elements to the end of a vector has, you know, a chunk of memory that it can use to hold elements. We keep adding new elements to the end of an array. Eventually we run out of memory. And what the vector does then is it goes to the operating system, or technically uses this allocator thing, goes to the operating system and says, can I have some more memory? Reserves twice as much as it had before. So if it previously had enough space for 10 elements, it'll go and ask for enough space for 20 elements. And then it'll copy or move, in fact, all the elements from its previous storage, move them into the new storage, and delete the old storage. And this process of asking for twice, somebody's bound to correct me online. I know not every standard library implementation uses that factor. I think libc++ uses a factor of 1.5, but still, let's just say double. Using that factor allows you to, in effect, amortize, that is, sort of average away this cost of going to the operating system and asking for some new storage and doing the copies. So it's pretty clever. But that's only adding elements to the end. If we add elements to anywhere else in the vector, then it's linear in, I said the number of elements in the vector, that's a little bit of a simplification. It's linear in the number of elements between the one we want to insert and the end. So if we insert right at the beginning, that's very expensive. If we insert one from the end, it's not too bad. And the reason for this is, as I was talking about last week, you can imagine a vector as being like a row of terraced houses, right? So adding a new house onto the end of this row of terraces is pretty easy. We just have to build a new house. But if we want to add a new house in the middle, well, that's pretty costly, because we've got to knock down half the houses, build our new house, and then rebuild all the houses that we used to have, right? So inserting things into the middle of a vector is expensive. That's pretty much the only thing the vector's not good at. It's the only bad thing about vector.
What happens when you sort the vector?
What do you mean?
Like, can you sort the vector inside?
Yes, you can sort the elements in a vector. It just switches them from one place to the other.
So it's not as expensive as inserting.
Sorting doesn't insert anything. It just swaps two elements over, swaps the values of two elements.
Oh, okay.
It doesn't actually do any like construction, it's just assignment.
Okay, thank you.
So the iterators of a vector are random access. So last week we were talking about iterator categories. I said that random access iterators are the most powerful kind of iterators. The ones that allow us access to all of the algorithms that are in this standard library. So random access iterators are great. They allow us, they have the most facilities. And so vector iterators are random access. And in fact, guaranteed to be contiguous in C++17, but that's really a detail we don't have to worry about. The most important thing probably on this slide is this last line, is that standard vectors should be your default sort of go-to container in almost all cases. When in doubt, use vector. Because for almost anything you want to do, except adding elements in the middle, for almost anything you want to do, vector is going to be faster than anything else. This is particularly true with modern CPUs because vectors are very efficient at using CPU caches as well, for those who care about those sorts of things. So last week we also talked about standard list, which, as I said, is a doubly linked list. So a linked list consists of nodes. Each node holds the value, and also a pointer to, that is, like, holds the address of the next node. It's like a chain of nodes. Each node holds the address of the next one, holds the address of the next one, holds the address of the next one. And in fact, it's a doubly linked list, and that means that each node also holds the address of the previous one. So we can move forward through this chain of nodes, and because it's doubly linked, we can move backwards through this chain of nodes. And this means that adding or removing an element anywhere in the list is a constant time operation. Because if we have each node holds the address of the next one, well, we just create a new node, and then we just change a couple of pointers. So this one points to the next, and back, and then this one points to the next, and we change the back pointer to point to the new node. So inserting an element anywhere in the list or removing is constant time.
But if you have to add something and you need more memory, it's going to take the same time.
Sorry, say that again.
If you have 10 elements,
Yeah.
and you want to add the 11,
Yeah.
so you want to ask 10 more spaces of memory.
No, so a list allocates each node individually. So if you have 10 elements and you ask for one more, it'll just request the memory for one more element, or space enough for one element for the value plus 2 pointers.
It's not the same as a vector.
No, a vector sort of pre-reserves some space in case you might want it.
In a vector, they all live next to each other. In a list, they're just randomly dotted around them.
So this is the good thing about vector. The first bullet point is about list, sorry. The first bullet point is a good thing about list. Everything else pretty much is a downside. So if we want to access a particular element, if we want to access element number 5, we have to begin, we don't know where element number 5 lives, we have to begin at the beginning of the chain and work our way up to number 5. If we have 10 million elements in our list, well, and we want to access element 5 million, well, we've got to begin at the beginning and count our way through 5 million elements. And that's a very slow process, and it's particularly unfriendly to CPU caches, and it makes iterating over lists a pretty slow operation.
Can you still do the square brackets?
You can't, no. So list does not have the square brackets operator, because that would encourage you to use it. And you don't want to use it because it's a slow operation. So vector has a square brackets operator because for a vector it's fast, it's constant time. But list deliberately makes it awkward to do, right? To discourage you from doing it.
So you have to use
You could use an iterator in a function called standard advanced or standard next, but it's going to be a slow operation. You really want to avoid doing it if at all possible. Or to put it another way, if doing that is important to your program, then list is probably the wrong data structure to use. A list, so if we want to access a particular element, that's slow. However, if we just need to know, yeah.
Do you mean a use case? Why you would use it? I need to allocate 5 million elements, and each of them are, say, 100 megabytes in size. So that's 500 times a million, right? So that means that a computer, if I use a vector, would need to have a single continuous chunk of memory that would fit all of them. Whereas, maybe there's another program running that's in the middle, so now I don't have that much contiguously. So if I use a list, it doesn't matter anymore because it will just take fragments. So, if you think of the concept of hard drive fragmentation, this allows fragmentation.
Basically, if you have some, to add to that, if you have some algorithm, something that you need to do that involves frequently inserting elements into the middle of a list, then that's a good choice because that's an operation that's very slow on a vector. There are a couple of other benefits to a list that, in particular, what we call iterator stability, but it's a bit complex to go into now, and they're kind of specialized uses. So iterators are bidirectional. That is, a standard list iterators are bidirectional. We can move forwards and we can move backwards, but only one step at a time.
Size is constant time. Does it mean it's calculating it as it's
Yeah, every time you insert an element, it increases the size. So the list holds the variable that knows the size. This did not used to be, well, was not guaranteed to be the case prior to C++11. And there are good and bad reasons as to why you might want the size to be a constant time operation. So I mentioned this already, but standard list is node-based. That means that each and every element requires a separate dynamic allocation, and it means that the memory for the elements is not contiguous. That is, this node will live over here in your computer memory, and that one will live over here, and that one will live over there. And it means that when we're writing a loop and the CPU wants to visit your program wants to visit every element, it means your CPU can't predict the memory access pattern. Right, so as I said last week, think about the postman who has a list of addresses all over the city, and he doesn't know what the next address is until he's visited the previous address. Right, if he has to deliver 50 letters all over the city, that's going to be vastly slower than just walking down one row of 50 terraced houses, chucking things through the letterbox. Right. So my guideline, you prefer standard list to standard vector only when you're frequently inserting and removing elements from the middle of a large sequence. If you've only got 10 elements, vector's probably still going to be faster even if you're inserting in the middle.
One more thing, list can only be a one type.
No, a list is a class template the same as a vector. So you can have a list of floats, you can have a list of ints, you can have a list of strings.
The container itself can only be a one, as in it can only be
Yeah.
list
All-
of floats or list of...
Yeah, all of the C++ standard containers are containers of one type.
Yes.
They're all homogeneous containers.
Could be your type, which contains lots of different.
Well, you can use your own custom type if you have, if you've written a person class, then you can have a list of person, or a vector of person, but you can't have, the different elements of a list can't have different types. You can't have, this node is an int, and this node is a float, and this node is a bool. That's, no.
But if you have, let's say, your class, and then you got, let's say, height, which is int, then weight, which is, let's say, count, or you have string, so all that will be still within your class.
Yeah, those would be elements of your class,
Yeah.
but then your vector would hold, sorry, your list elements would be your class. You could have a standard vector of standard list, if that was appropriate to your application, yeah.
Standard vector of standard vector of standard vector of standard list.
Something else.
Yeah, if you really wanted to. So the final sequence container I'm going to talk about is something called deck. It's a double-ended queue. So what are the properties of one of these mysterious deck things? Well, element access is constant time. That is, as for a vector, accessing element 10 is takes the same amount of time as accessing element 10 million, if we have that many things in our deck. As with a vector, insertion or removal of an element at the end is a constant time operation, amortized constant time. What DEC also gives us is that inserting or removing something at the beginning is also a constant time operation. So with vector, it's only at the end. With a DEC, we can insert at the beginning as well, quickly, in constant time. That's why it's double-ended. And as for a vector, as with a vector, inserting or removing elements anywhere else, inserting or removing elements in the middle is slow, because we've got to knock down lots of houses and rebuild them. That is, move our elements, destroy them, rebuild them. And as with a vector, iterators are random access. That is, they have all the properties that it's possible for an iterator to have. We can use them in all of the operations, including all the sort operations, which generally require random access iterators. So you might look at this and go, well, hang on, these properties are pretty much the same as the ones I just put up for vector a couple of slides ago. Except that DEC has this added facility that we can also add things at the beginning in constant time. So, hang on, surely DEC's better because it can do everything that a vector can do, plus we can insert at the beginning in constant time. Why don't we just use DEC everywhere? Why does vector even exist? And the answer is, unfortunately, there's no such thing as a free lunch. This facility of being able to add things at the beginning in constant time has a cost. And the cost is that it takes fractionally longer to access element 50 than it does to access element 50 of a vector. Right? It's not a very big cost, it's not a very high cost, but it's there. In fact, pretty much all of the operations on a DEC are just very slightly slower than they are for a vector.
Why is that? I thought it's just a vector which is double-ended.
Well, the way it's implemented is sort of as a vector of fixed size vectors with a sort of floating one at the beginning and a floating one at the end. It's a bit complicated, but effectively we have to work out which of our inner containers we are and then give you the offset to that inner container. So there's an extra operation. It's still constant time, but there's an extra operation that we don't.
Does it dynamically expand?
It does, and it expands from either end. That's why it's a double-ended queue. We can make it bigger from the end, as you can with a vector, and we can make it bigger from the beginning, which is unique to a DEC. So they have, although all these operations are constant time in this, so they have the same algorithmic complexity that we'll talk about in a minute. They have a larger constant factor. They're very, very slightly slower than the equivalent operations on a vector. So C++, we really care about efficiency. So we'll tend to use a vector when we can and use a DEC only when adding things to the beginning is appropriate. For example, if you have some sort of queue where you put new things into the queue at the beginning and you pop things off the queue at the end, that's something, that's basically what DEC is designed for. You could, in fact.
Stack is basically just a subset of what you can do with these containers. In fact, stack is templated on by default vector of DEC, isn't it? Actually?
Stack is in fact one of the container adapters that we'll talk about at the end. You can look up, I think it's a vector, isn't it? It's built over. You can have a look.
It's either vector or DEC, but it's not actually a container in its own right. It just wraps a real one and restricts what you can do.
So those were sequence containers. Yes?
How do these properties translate into 2D arrays? Are there any? Is it significantly different, or does it just add a little bit more complexity?
So C++ doesn't have any two-dimensional data structures in it. Right? So if you want to have, say, a matrix class, like 2D data structure, there are two common ways to do it. And the first one is to have like a vector of vectors. Right, so each row in your matrix would be its own vector. And the other way to do it is to write some sort of wrapper class and just allocate one big vector of like n times m elements, where n and m are the dimensions of your matrix, and then handle calculating the offsets yourself. And that's quite a bit more work, but has the advantage that you only have one allocation to worry about, and you don't get, you're not jumping over memory and things. But no, unfortunately, C++ doesn't have built into it any sort of two-dimensional data structures.
Just if I may add, because I've seen it once, at least with an array, that you can declare it, or with the declaration, you can two square brackets behind each other.
Yeah.
And then it sort of behaves, or you access the elements. Like
Yeah. So that's a common thing to do in C, that you can, because the C syntax makes it look as if it's sort of one 2D data structure. It's actually not. So what happens in the C language there is that what you're actually doing is you've got an array of arrays, and then if you've got a 3D, like some sort of tensor, you've got an array of arrays, right? And so the way we do that in C++ is to use this standard array. So you'd have a standard array of standard arrays of ints or floats or whatever. And that would exactly replicate what C is doing. And you'd be able to use the same, square bracket syntax to access a particular member. Yeah.
So without sounding stupid, all of these things are conceptual as such, and they're not real things. Because could you not implement a DQ of an array if you wanted to? It wouldn't be very efficient. Or you could even a vector. You could kind of do it with.
You could add like the deck has a member function called push front. It's like pushback, right? And yeah, conceptually, theoretically, you could add a push front member function to a vector, right? But because of the way the data it's structured, that would involve like destroying all the elements, putting this new one, and then rebuilding all the elements that you had. So for a vector, that would be very slow. So yeah, you could, in principle, give it the same functionality as a deck, but it would be slower.
So basically, these would be implemented for optimization. So these things work very well
For the particular things that they're aimed at, yes. Yeah, absolutely. That's why I said, if you want something that's like generally good, use a vector. List and deck are useful for their particular things they're specialized for. In the general case, use a vector. Yeah.
So generally use a vector.
Yeah.
But as your need arises, you use any one of these data structures.
Yes.
So which one offers you the best solution for your problem?
Exactly that. That's why there is this variety of them. Absolutely, precisely.
You cannot use a vector to do a tuning function. Effectively, you'll be better off to use it.
Exactly. So this is a specialized container that is good for that purpose. You could use a vector, it wouldn't be very fast. So in that circumstance, yeah. So think about it, the vector is the good general case one, and these other ones, set and deck, are the ones that are good for specialized usage. So those were the sequence containers. Those are the ones that store all their elements in the order in which you put them in. Right, they're just a sequence of values. We also have a selection of what are called associative containers. Associative containers associate a key with a value. Well, sort of, anyway. Key value pairs, things that other languages call dictionaries. Object if you're into JavaScript. In C++, the equivalent is a standard map. So it's a collection of key value pairs. And we sort these elements based on their keys. So they're stored inside the map in order of their keys. And that means that when we search for the value associated with a particular key, we can look up that key very quickly. There's a similar data structure called a set, which I'm now going to be very careful about how I pronounce.
It's the STD, SET.
Yeah, that one. And a set is basically like the map, but without the values, right? It just stores the keys. So it's keys, but without an associated value. And in a set and in a map, the keys must be unique. We can only have, if we have a map mapping strings to ints, and we have the string 1 and then the int 1 and the string 2 and the int 2. Well, we can't have two copies of the same key. Can't have two copies of the key 2 with different values in our set or in our map.
So is the key value pairs, are they sort of stored in the vector?
No, they're stored in something called a red-black tree.
Okay, like there's that.
Yeah.
A red black tree is a form of B tree, yeah.
You sure about that?
Yeah.
Oh, okay.
Tree. It's just different.
What is a key pair? I don't know. I've never used it. I don't know anything.
Something like that.
Yeah.
You know that you have a dictionary, literally you have a dictionary, you
Yes.
have a word, and the word is associated with a unique meaning, what with the meaning. So usually in the dictionary there's only like one term, isn't it? You don't usually go and say dog and then there's another dog and another, just dog and has different, it gives you all the explanation of dog.
Yeah.
Because the dog is a unique key, isn't it? It's just like if you have a PIN number, your PIN is unique and have the information next to it. So it's like a unique key and the value associated with that key.
So there's only one value to it.
Yeah, so what I don't know, but in Java when I did it before, if you try and put the same key, it overwrites the previous key.
Yes.
It doesn't complain, just overwrites
So
it.
there's a
Yes.
one-to-one mapping.
Yeah.
It's
Doesn't
a
have
map
to be.
from keys to values. So
But there's only a one value to one key.
It doesn't have to be.
Okay,
You
it
can
could be
always
like one
want-
too many.
There's always one key.
Yes.
Always, always, always. But there's a multi-map, and there's multi-map, multiple values for one key if you wish.
Yeah.
But you could equally just do an unordered map, a map of some key, a string, and the value could be a vector. So you can have the key is a string, the value is a vector of something else. So you can implement it yourself if you wish. You don't have to use something like multi-map, but it has some benefits in certain cases.
So map and set are the ones that are commonly used. There's also multi-map and multi-set, which are a bit more complicated and let you have duplicate keys. I'll be honest, I don't think I've hardly used either of those. They're not very commonly used, but map in particular, very heavily used. Set comes in handy sometimes. Multi-set and multi-map.
When would
Again-
you use maps?
Anytime you need a mapping from something to something else. So imagine that I wanted to save the scores. So I gave you all a test and I wanted to save everybody's score. I might create a map from string, which is your name, to an int, which is your test score. Right? And then I can look up in the map, I can look up what was Tom Brezza's score and it will tell me.
Would you be able to use it, so let's say like in a situation like that, but if there is multiple scores, so let's say you have, I don't know, 10 scores.
Well, if there were 10 people in the class called Tom Brezza,
No, there is, let's say you have 10 exams for Tom Brezza.
right?
So how would you store that?
Well, then you might have a vector. Your key type, sorry, your value type might be a vector of exam scores.
Think of a set and map as a way of finding a needle in a haystack, right? So you fill it with tons and tons of elements. The key is your needle, and it's designed so that you can find that needle in the haystack really fast. It's like a magnet.
I'm asking because that's day 4 is on my radar.
Advent code.
Let's talk about map. A map, as I just said on the previous slide, is a sorted container of key value pairs. Unique key value pairs. That is, every key has an associated value, and the elements are stored internally in a particular order based on the key. This means we can access elements inside the map in what's called logarithmic time. Depends on it grows with the logarithm of the number of elements in the map. Right, don't worry too much about the mathematics if it scares you, but basically this means it's pretty fast. Right? That is true, and I will talk about that in just a moment. So, iterators are bidirectional. That is, we can iterate over our map, and we'll iterate over the keys and values. So we'll get key value pair 1, pair 2, pair 3, in the order in which the keys are stored. And we can move backwards through these stored keys and values as well. And iteration order is well defined. That is, every time we iterate through it, we're going to get our keys and values in the same sorted order. As I mentioned, this is typically implemented as something called a red-black tree. This is data structure you can go away and Google if you're really fascinated by these computer sciencey things. So keys are sorted using this thing called operator less by default. So when you said not every type can be a key, that is true. It needs to have a less than operation defined on it. It needs to have some way of saying, I can order these keys in some way. Right? So for ints and for floats, this ordering is built in. There's a built-in ordering for ints. Right? There's a built-in ordering for floats, which is a little bit weird, but works mostly the way you think. And for strings, there's the standard string implements this operator to say this string is less than another string. So we can have keys that are strings. Yeah?
Can this order be changed?
Yes. So if you have a map in which the key type is some custom type that you've written, you can implement this operator in any way you like, any way that makes sense for your class. The other way of customizing it is by specializing one of the template parameters. So I mentioned this at the beginning, that these are things called templates. Templates like a blueprint for how you construct the class. And the template parameters are the key type, the value type, and there are a couple of others in fact, but one of them is the compare template parameter. That is how we compare the operators. And by default this uses the less than operator, but you can get it to use other operators or other functions if you prefer.
It wouldn't be feasible after the map is initialized.
No, you have to do it when you first create the map, when you first define the map, because it's part of the type of the map.
It's also worth mentioning that keys are const in map and set and the unordered ones. Once you stick key value pair or key into one of the containers, you can't modify them. You can't read it and change it. So you can take it out of the map, put a different one in, or modify it and put it back in, but you cannot change it while it's living inside the container.
Yeah. So once you've added a key value pair to your map, you can change the value. That's fine. You can change the value associated with the key. You can't change the key because if you did that, you would change the sorting order, right? So what you have to do is remove that element and then add a new element with the new key, just to maintain that sorted order. Sorry, say that again.
Can you use vector type to be your key?
Can you use a vector type to be your key? I think you probably can, yes, because it implements this less. I think it implements this less than operator. I'm actually not. Now I think about it, I'm not 100% sure. You could certainly write a custom comparator function that would work on vectors. It does. Okay. So yes, I'm pretty sure you could use a vector as a key type if you wanted to.
Not in an unordered set or unordered map, but in a map or set, yes.
Getting back to the basics, why are we sorting these?
Because it allows us to find a particular key very quickly in logarithmic time. So if things are sorted, we can do a sort of divide and conquer, binary search as it's called, to very quickly find the right, where this key lives in memory. Sorry, did you have a question?
Yeah. So can you use your own types as a key? So using operator overloads or something.
Yes, you absolutely can. So if you overload this less than operator, I think you also need to overload the equality operator. As long as you overload those operators, then you can use your own types as a key.
Only need less than.
Okay. You only need to implement the less than operator. You only need to define what it means for one of your type to be less than another. So imagine if you had some sort of person class, you might sort based on the surname first, and if two people had the same surname, then you might sort on the first name. And that would be a way of defining and ordering for your class.
It's also important to mention that your less than operator must act as if it was comparing cardinal numbers, right? So 1 is less than 2 is less than 3. You must never allow two different things to compare and both say that they're not less than each other, or right? If you do, it will just delete one of them.
Yeah. Sorry, yes.
Sorry, the reason we're, because I know how the trees work. Like
Yeah.
This is less than put that there, this is less
Yeah.
than. So is that what they're using in terms of how they store it? You need to know how the less than operator is sorted, because you need to know where one thing is in relation to everything else.
Exactly that, yeah.
So what if the keys are strings? How would you compare less than?
So you can look at how the less than operator is defined. It's something called lexicographical ordering.
It's default.
Yeah, that's the default sort order for strings. So basically,
By all
it looks at the first character that differs in the string and then compares alphabetically which one's first.
Is it based like on the ASCII table? You have like
Yes, it is actually. Well, technically based on the byte values, but yes, like the ASCII table, yeah. In my opinion, the standard map should be your default go-to associative array type, that is your dictionary type, your map type, the one you like best.
Quick note for everyone: if you don't know what O log n means,
Hang around.
I've linked to a fancy visual chart on our Slack and on YouTube that's live streaming, so feel free to look at a visualization of complexity.
Sorry. So, whenever you need a mapping from one type to another, say like I was suggesting storing a list of names and scores, an associative array, standard map is a really good choice for that. You can't go wrong with it. The other one I'm going to talk about is standard set. You can basically think of standard set as being a map without the values, right? It's just the keys. You think, well, why would that be in any way useful? It's because elements are guaranteed to be stored in sorted order all the time. And more importantly, standard set guarantees you have a collection of unique elements. So if I have a standard set of ints that contains 1, 2, 3, 4, 5, and I try to add 3 to it, it's going to say, no, I already have an element, I already have a key of 3. Right? And you can check the return type of the insert function. It will say, well, I didn't insert this because it already lives there. It already exists. So standard set is really good for ensuring uniqueness.
Can you cast something to a set?
No, but you can copy things into a set if you want. But there are more efficient ways of doing that. There's a standard library algorithm called standard unique. So standard set, again, is implemented as one of these tree data structures. You can often, not always, but often get better performance by doing what a set does, by doing it, by having a vector and keeping it sorted yourself. Because of all the nice properties of vector that I've talked about before, about having this contiguity of having all the things laid out next to each other in memory, means it's really quick to zip through all the elements. Whereas a set is a node-based container, like a list, meaning that the values, in this case the keys rather, are spread out all over memory, so it's slower. We have to roam all over our computer memory in order to iterate over all.
So what's the point of using it?
Because insertion is constant. It's basically like a sorted list, more or less. So it has the same, roughly the same properties of a sorted unique list. Yes, the elements in a set are always sorted. Sorted according to this operator less that we talked about before. So we talked about sequence containers. We talked about associative containers, which for some reason standard set doesn't really associate anything with anything else. It doesn't have a key and a value. It just has keys, but it comes under this same banner. And we also have these strange things called unordered associative containers. We have unordered map, unordered set, unordered multi-map, and unordered multi-set. So exactly the same as we had before, but with this word unordered before. What are these then? Well, the one that is used most often is standard unordered map. And this is the C++ standard library's version of a hash table. So again, pretty much every language that you will use, or the standard library for every language that you use, will have some notion of a hash table. I don't know why they called it unordered map and not hash map. They really should have, but there we are. So an unordered map is very, very much like an ordered map. The interface, the program interface, is almost exactly the same. But it has very slightly different trade-offs. Yeah, were you going to say something? Oh, you looked like you were trying to get my attention. So for a map, element access is in logarithmic time. For an unordered map, on average it's faster, but sometimes it's really slow. So for a map, it's pretty fast all the time. For an unordered map, sometimes it's very fast. Very occasionally, it can be very slow. Yeah.
But when you're looking at ordered map, don't you have to do the overhead of sorting in the first place?
Only at the point where you insert into the container.
Yeah, but if you insert a lot, isn't that a big overhead?
It can be, but for this, as you're about to see, you have to compute the hashes for everything anyway. Yeah. Nothing comes for free, unfortunately. Yeah. So iterators, we only have forward iterators. We can iterate through the container as you can with all the containers, but we can only go forward. This means we're restricted in which algorithms we can call on elements of an unordered map. Iteration order is unspecified. This means that if we have some things in an unordered map, we add a couple of new things, everything might have moved around, right? It's unordered. We have absolutely, the elements can be given to you in absolutely any order whatsoever. Whereas with an ordinary map, an ordered map, when we iterate over the elements of the container, we're guaranteed to be given them in the sorted order of keys. For an unordered map, we're guaranteed to get every element exactly once, only once, but which order we get them is unspecified. It's unordered, hence the name. So compared with standard map, we have this potential benefit of faster lookup. Potentially. With the occasional worst case behavior. But there's a downside. And that is it's a hash table. So we compute a hash of the keys, and we use that, well, to put the value in a bucket, but it doesn't really matter. It uses this hash to decide where things live. And so every time we add something, we have to compute the hash, which can, in some cases, be more expensive than just doing the ordered lookup. Yeah. Okay, so a hash is like, how would you explain this?
I got this.
Oh, go on.
Yeah. So a hash is something that you have some quantity of data of an arbitrary length, and it will digest it, hash it, into a fixed size, which is typically smaller than it actually is. So that then means that for any given length of data, right, I'll digest it down into this smaller size, and I can use that as a lookup key once I've done whatever processing to get there. That does, of course, mean that different pieces of data might end up with the same smaller value. Those are called collisions. So to resolve those, it means that if I do end up going, to my smaller value, and then looking in that spot, and there's actually, there's two things there, not one, then I have to see which one of them is the one you actually want. So if there's 10 of them, I've got to go through the list until I find the one that matches what you want. If there's only one, it's instant.
So it's a bit like URL shortener.
Not that has to be unique. You go to the wrong place otherwise.
Sorry, so if I understood this before, like you can have a hashing function that takes some information that you have.
Yeah.
Based on information, create something that's unique.
Creates, it creates, let's say, a number. Right? Let's say it's 256-bit number, big number. Right? And it uses that number as a sort of index into this unordered map. And so every time you, what is that? Every time you add an element, it has to compute this hash. So it has to take your string, do all the processing, and compute this number, this hash value. Yeah.
So, just so I don't get confused, in an ordered map, do we supply the key?
Yes.
In a hash table.
No, in a hash table, we supply the key as well. It's still a key value store, except that behind the scenes, it does this hashing thing and uses that hash value in order to store the keys. Yeah. Oh, sorry. Two of you with hands up.
Does it also mean that you have to maintain this other lookup from the hash to the index to where it is actually stored to maintain it? Does it become bigger than the address?
Well, that's the hash table data structure, right? It's a mapping from the hash values from the hashes to the value of the thing you stored.
But it decreases the memory, right? Because if you have hash functions, it increases it's quicker lookup.
Yeah.
Does it also the storage of the hash?
All right. So if you have this equivalent number of elements, will an unordered map use less storage than a map? I'd say it's probably going to be about the same. I've not done any comparisons. I can't imagine that it would be any different, to be honest. Yeah.
Isn't it possible that you then end up with errors where maybe a key is associated with the wrong value because on accident you have a collision?
No, so when you get a hash collision, that's perfectly fine. Well, no, ideally it never happens, right? That would be a perfect hash. Sometimes it happens, and when that happens, it's dealt with. They know how to deal with it. It's fine.
That's one of the worst cases.
That's when you hit worst case behavior. Yeah, absolutely. So there is this function. It's actually a function. Sorry, was there another? There is this function object called standard hash in the standard library, and that's what is used to compute these hash values. And this thing of standard hash is well defined for all the built-in types and for most of the standard library types. So if you've got an unordered map where the key is an int or a float or a string, any of those types, then that's going to be fine. The problem with unordered map comes if you want to use your own type as the key. Because for an ordered map, if you want to use your own type as the key, it's really easy. All you have to do is define an ordering using the less than operator. For unordered map, if you want to use your own type as a key, it gets a lot more tricky because you have to implement a hash function. And that is very definitely a non-trivial thing to do in any sort of way that generates a good hash, right? It's a hard thing to do. So that's why I say standard map is probably a better to use in the general case, because it's much easier to be able to use your own types as the key in a map than it is in an unordered map, because you really don't want to be writing hash functions, right? It's not a fun thing to do unless you're sort of some strange security-orientated mathematical type person. If you just want to get on and get stuff done, writing a hash table is not something you want to spend your time doing. And yes, performance is highly dependent on the quality of the hash function. That is, if you've got a poor hash function that generates lots of collisions, you're going to hit this worst case behavior very often. There are also security implications based on deliberately generating hash collisions. This was an issue that hit Python actually a few years ago. Yeah.
It's a hashing, by the way, dynamic. I imagine that when you have various keys that you use, for example, when you only use integers,
yeah,
you probably can hash them very easily to to hash values that are that just take up a very little space. But if you happen to have strings that you need to hash, probably there's a lot more. The hash value must be longer.
No, so the standard hash always returns a 64-bit integer.
Isn't it?
Well, size T, so it depends on the platform.
Oh, that's true, actually. Yeah.
I don't know how to say English, but I guess it's like taking the sledgehammer to a mouse.
It's generally quite so. So this is a whole field of research in what's referred to as cost per byte, right? So how many cycles of the CPU does it take to process one byte? So the standard doesn't dictate what implementation is used, but I happen to know that I believe it's murmur hash 2 that is used in libc++. So there's various different hashing algorithms. Some achieve a cost per byte of a few cycles, which is incredibly fast, obviously. If you think you've got a CPU that's 3.4 gigahertz, you know, 3.4 billion cycles, right? And a few cycles per byte is nothing. But yeah, I believe it's murmur hash 2. There's a whole field of research into that. And you can implement your own hashing algorithms in C++. It doesn't force you to use the ones in the standard library. So if you can do better, you can.
And prove them wrong.
So another thing I'm thinking about your hash function. If you can't test it rigorously, it could work for years, and then all of a sudden do madness because it hasn't been through the things.
That would, so if you screw up the hash algorithm somehow, it will just make things slower. It won't make things incorrect. What it means, an ideal hash algorithm will minimize collisions, right? When you use an unordered map or set, it first of all does the hash to find the elements, could be more than one, that matched for that digest. And then it will do an actual quality comparison to find out which one is the real match for what you want. So by having collisions, by having a bad hash algorithm, you just make it slower. Because imagine each unique hash value is like a bucket. Okay, think of it as a bucket, and you stick stuff in the bucket, right? So ideally, if you have one value per bucket, that's really good because you say, I want this thing. Okay, we hash it. We go to this bucket. There's only one thing in the bucket, so it must be this one.
But I would have thought, sorry, don't mean if you had two different values and they hashed to the same value, instead you've got a many to one relationship, I would have thought that would be a problem because one's the one that you wanted to keep.
No, because you hash them, you go to the bucket, they're both in the same bucket, so now you compare them. So imagine 5 and 6 ended up in that bucket. I asked for 5. Does 5 equal 5? Yeah, it does. Okay, there goes 5. If I picked up 6 first, does 5 equal 6? No, it doesn't. Put it back in the bucket, get the other one out. Is that 5? Okay, that's the one you wanted. There you go.
So all it is a performance issue. It's not correct.
So once you go down into a bucket, you then do a linear search until you get the one you want in that bucket, right? So I keep picking stuff out of the bucket till I get to the one I want. It's just a linear search after that point.
So it will behave as normal, but it'll be very slow.
If you get loads of collisions, it then makes it slower.
If you use it in a sense that you have like a fixed list, for example, how many countries we have left,
Yes.
then it will be a perfect solution because you have O of 1 instead of have a logarithmic function, which exponentially can go up. So that's when you use the hashes, and that's when you don't use the hashes. If you put the hash algorithm that you put all the countries in 10 packets,
Yes.
so then it's going to be very slow.
Absolutely.
That's if you're dealing with data that's constant, isn't it? Like,
Yeah.
the number of countries stays constant.
No,
Yes.
no,
Dynamically changing, you're not going to use that.
no,
No,
you
because-
don't want to use the
yeah.
hashes.
Yeah. No, that's very good.
Yeah.
So this is unordered map. There is, as I said in the previous slide, there's also unordered set, which has the same relationship as map as set does to map. So an unordered set, you can think of it as an unordered map, but without the values. It just stores the keys, and it does it in exactly the same way. It hashes them. It's got, constant time lookup on average, linear worst case, forward iterators, unspecified iteration order. It's like a map, but without the values. And there is also unordered multi-map and unordered multi-set, which I've got to be honest, I have never ever used, but they're there, available for use if you have a particular need for them. And just finally, just very quickly, I've talked about sequence containers, associative containers, unordered associative containers. The last category I had on the first slide there was talking about container adapters. So container adapters operate, or they wrap, I should say, sequence containers to give them a slightly different user interface, slightly more restrictive user interface. I've included them here for completeness. In my experience, they're not very heavily used because the adapted classes, the wrapper API doesn't have begin and end functions on it. So the wrapped classes are not containers, strictly speaking. You can't iterate over them. So to my mind, they're not very useful, but they exist, and I thought I should tell you about them just for the sake of completeness.
Did you say something about heterogeneous lookup?
No. That's it.
Someone made a comment that containers don't yet have heterogeneous lookup, which is true, but I didn't think you said something about it, but just checking.
So there's this adapter called standard queue. So we talked about standard deck as a double-ended queue. There's also an adapter called standard queue, and that's a first in, first out queue. And a standard stack, which I think you mentioned, yeah.
But if it's a class, we should be able to access the container in the class.
There is a member function that will give you the wrapped container, and you can iterate over that. Yes, correct. Quite why they don't expose the begin and end, I don't know. Probably because it would let you change the values and mess about with the properties. I don't know. If you haven't got the sense yet, I don't particularly like these, right? So, don't think I've ever used them. I'm just aware that they exist, and
Never use stack.
I don't think I have. Why would you?
Because you want if you're working in a team, it's a statement of intent that you can stick stuff on the top, pop stuff off, and the point is that you shouldn't be using that thing in any other way. It's designed for that one particular case. Statement of intent.
Okay. So yeah, there's a queue, a stack, and this funny thing called a priority queue, which keeps the elements of your container in a partially sorted order. So it always gives you constant time access to the largest elements. Doesn't bother sorting all the rest, it just finds which the largest is and keeps that in a position so that you can get at it readily.
Is that just the first element in the priority queue?
So if you think about it, if you wanted to, if you just had a vector and you wanted to know what the largest element was, there's no way of doing that other than iterating through, looking at every element and seeing which one's the biggest, right? You could use a set, because a set is always sorted. So then you could say, well, it's always this thing at the end, because that's the largest. But then you're sorting the whole container, that's extremely expensive. So priority queue is a sort of hybrid thing that just does a partial sort just to keep the largest element at the I can't remember if it does it at the beginning, at the end, but keeps it so that you can always access the largest element. Right, I've been nattering for quite a while. Let's get you guys to do this. So who was here last week? 3, 4, 5, a few of you. I didn't get as far. This exercise was going to appear at the end last week, and I didn't get as far as setting it for you guys. We didn't quite reach the end. Those who, and I know there were a few of you who went hunting on our Get site for some homework, will have come across this and will probably have already done this exercise. So you get to, put your feet up for 10 minutes. I only want you to do exercise 1. There's a second exercise there as well, which is also, it's a pretty good exercise. I didn't come up with it, I borrowed it. But exercise 2 is also a good exercise, and I'd recommend you do that at some point on your own time. But just for this session, if you can go to that URL, check it out, and do exercise 1, please. Oh, and as always, if you have any problems, then put your hand up and I'll get one.
Yeah, me to do it.
Ollie,
It's up to you.
can I try that with me, see if it works?
Yeah, let's try. Very nice, effective 0 date on that, so just plug it straight in and I'll give you bank details. It's up to you. Just shut the computer down first. Yeah, like I suggest shut it off and then plug it in. Because you want to boot from it, it doesn't open.
That way you make sure that your
Also,
device
yeah, I need to check the boot sector.
Check.
No, I got it.
Christ, can we get the compiler out? Can't leave that.
Oh, you want to go to the toilet? You need, Ollie needs to.
Okay.
He can let you back in.
Oh, you can go, and then we just let you in. So just go.
Oh, okay.
I have more.
So yeah, I did exercise 2 from last week.
You did what?
was doing exercise 2 from last week, this week apparently. So I've already done the one which we talked about last week. So I was doing this was door code access one.
Okay.
It's pretty fun.
Is there an F1, F2 delete? Try and too late, reboot.
Don't do it again.
I would spam F1, F2 and delete while it's booting.
I was not sure. It's not bad. It's a problem.
How was that laptop?
I was trying to work out.
So you just usually
Maybe Google what the HP this notebook
and then
boot load up.
oh no, we get
That's it. Yeah, I like the exercise 2 from last week.
Yeah.
It was good subtext, but you need to like create your own things on top. It's not fully explained, which isn't a good way because then you should really think about how does the door thing work and what other functions would you need.
Yeah, I thought it was a really good exercise. Oh, those are underscores, by the way. Sorry. Yes, sorry. It's SQL underscore week 4 underscore classes.
anyone else having trouble? Or you were saying something?
So I'm just saying how I like this exercise.
10 key. Do you have to hold down function on that keyboard to use function keys? I think so. I'll try both sometimes. Sometimes with booting it's not on. This is already a project. It's probably paste it to file. It's probably better if you open it. Oh, just open it.
Maybe they're disabled as you can't access the menu unless you admin. Disabled person.
No, I thought we were talking on the same. With this thing, what we're going to do is nearest neighbours like the first person.
And it was asked why should it cost the area
What was it?
Just
set.
yeah, it's a structure called KD tree.
Alright.
Okay.
So you can open.
Which is
We don't need to create plants.
Across the set points.
In your main fucking your main.
Okay, say KD.
KD tree.
K-dimensional tree.
We should change that.
No, it's the public buildings.
That's just for the back. Maybe talking nonsense. That's just
Well,
for the back.
and then you can just open it. Right, you got it there.
Right, where's it here?
You're looking at the remit, go to the root project, bold. Yeah.
No. Make this a little bit.
Generally, you can't say what I'm saying. What they'll do is fire blocks with your returns. It's very try holding your escape point.
Right.
You try to function F10 and just F10.
Try again. These guys.
Like hold this down while
Yeah.
slamming, like repeatedly hitting
Yeah.
Seems to make more sense.
the escape point. What model of HP is it?
It's a lead, but it's not. It's a lead point, but
Is there a model? Must be a model.
But they had arguments.
You have the right time right now.
Is there any arguments in
Let's escape to
No, you were
Right,
crossing
something
and
else.
then you had to implement class anyway.
Root menu. The middle one. They haven't.
this one.
Just exit that. It's because you get all the keys. It's now entering the management. Just go straight to the bottom and exit.
It work also with the mics.
Okay.
Sorry? Will it work with the mics also?
No, I haven't.
Very weird because they require me to call them just to install stuff. They're really annoying.
They won't know this is happening. It doesn't modify the system. Once you shut it down and unplug it, it doesn't touch the hard drive at all. I mean, you can install it to the hard drive if you want, but obviously don't.
No. I can't uninstall stuff that I installed it, and they ask me to because I'm not admin, they ask me to call them to uninstall it. It's like they don't know technology.
The thing is, because you were able to do that, boot from a USB stick, I can load a password recovery tool on it and just reset your things straight away.
Oh, you want? Well, actually, I'll probably
I mean,
get in big trouble. Like,
might get fined, so I wouldn't do it. It's really fine.
Yes, with the trick. So finding yeah, so blah blah blah.
Why is that?
Find
No. Where?
here. So I'm basically setting up here insert.
Yeah, equals stood begin.
So I was just creating so this all have to go for find, not like this.
What is the bit after the equal sign supposed to be? Because forget the big. What is the bit after the equal sign?
Here,
Yeah, what is that one?
well, I'm looking from the beginning to the end for this.
No, you're not.
Yes, I am.
No, you're not. All that is stood begin, stood end, sugar, and that's just the comma operator.
Find.
Stood right. Call the function. It doesn't have to be. It won't have to be cash. Hopefully by next week. So we're still setting up the company account. So if you don't have cash, I can give it to you next week. We should have the account set up by then.
So the trouble is what you've done is so you've copied each of your elements, you've copied things like those. But when you get to the end, there's nothing here. It's just a random bit of number. And it's really dangerous. In fact, it's designed to try and access this bit of movement and copy without being able to. So one way to do this is to find the element called
Yeah, I mean, if we're going out, yeah.
Yeah.
Might as well just,
Hold on to it then. You just go.
and then you can just move the last element. So that's basically the way it works. So finally, swap it.
wait, you want me to go now or like after the class?
No. When we all
Well,
go.
There's another company doing
Security female 90.
As I said at the beginning, this is all a bit like don't panic. We have built
Sit in, and do you code out?
most people at the same level. I mean, maybe a bit of experience in some
I
ways.
suspect the area.
No, you didn't.
Please don't feel overloaded. So,
It is. See, okay, this is what they posted on Twitter, and this is very much.
To be honest, it's not really intuition, that's deduction. You clearly got the syntax right, it's in my system.
This is how I feel frequently. Me learning C++, stage 1. Me learning stage 2.
Hey, Oliver, is it not possible to like go on the internet from this?
Yes, it should. Well, my bundle bit it's a pretty recent kernel. My bundle bit pretty much all the microns. So I would hope so.
With the Firefox.
Okay, so
Maybe we can always check the
what we're saying here is this is almost like B
yeah, Tom, do you still have more
assign it to the
licenses?
You didn't do vector, but we'll do it for you. So
I is not the same.
sensory.
You don't want to do B dot P and so it's not the standard string. What you're going to get is an iterator.
Just include that.
Iterator types are really horrible.
Don't delete the papers.
Do you want to?
Oh,
So yeah, Tom, sorry.
So
Go ahead. Do you still have more C lines?
I do.
Can I send you an email?
Yes, you can.
you need to complete and you've done you can't just
extension.
no. So the issue now is not that good. You can't just dump a vector into CM. You have to iterate over it. You can use range for well. Go back to the
that's what you wanted to do. So that's the right thing. So, leave it.
Right empty vector. I'll just write a function. Write a function, probably fancy, write an operator overlay. Write a function that takes a reference to
Question for you.
Yeah.
Would that be sufficient for you to change the thing in, or would you like to do this in a different way?
No, that's fine. Yeah. You don't have to. You can just put sugar in there.
I was playing because I was doing something wrong.
So that's really good. So
I did this. It was working for so
and then you place sugar in there. Yeah, because you're trying to remove the last element from an empty vector. You haven't just put anything in it.
oh yeah, right. You see, that's sorry.
So, two things about this. Scroll down a bit. F item. So this is the standard find is absolutely. What you've got to do is first of all check to see whether F item. So F item, the way find works is if it finds the thing, it's going to return you an iterator.
So basically, I should have
No,
if
no,
not
that's
equal to n.
yeah, absolutely.
Yeah.
If you really look for a function called standard replace.
I was showing Ollie this. We learning C++. Stage 1. Stage 2.
Yeah.
That's how I got it when I was doing this.
Oh, you're still doing.
Really
It's really good practice.
Standard replace, did you say, yes?
Basically giving the game away, but
Yeah. That's
So it replaces 8 with 88, yes?
well, strictly speaking, Tom, the question does say use a loop to.
Yeah, that's the reason I asked you, yes, whether you are happy with that.
That's right.
So vector A gives you an iterator to one position pass.
It's really important because then you can use an
There is
PC
an
and take it with you and travel or whatever. Use anyone else's computer and have the same environment.
Just trying to.
now Now, the next interview question, tell me why that worked. Binding R values to the L value references. So how are people getting on with that? Who has finished? Including the people who did it last week. Of the people who didn't do it last week, who's finished? Who's halfway through?
Who's completely lost?
Who has no idea what's going on? Well, at least you're on his side. Okay, I'll give you a bit longer then if people are still working on it. Because you have to put the declaration above when you get to so that's the one.
Yeah, later on.
I know. It's horrible, isn't it?
I haven't done much, but I have not even installed my system.
Ah, well, we've got a little memory stick you can use that you can just boot off it.
It will not fit on my.
Oh, you don't have a USB stick. You've got a fancy new computer that doesn't have USB.
You need a dongle. You need to pay Apple £50.
I can tell you how to install the system.
I downloaded C Lab. What did you do after?
Okay, so if you go to just bring up a terminal window. So do Xcode select. Oh, you've already got them installed, so yeah, you've already got a C++ installed.
But no, that's
But not, no, you haven't installed. So you need to download C Lab.
I did download it.
Okay, so if you install it, you should be able to locate your C.
Interesting if you try running Clang
That's
from
installed on the
Marmite, just Clang dash version.
Yeah, I have.
It doesn't ask for license.
It's installed.
Well, no, it can be installed for Apple, thank you.
I have just done Clang++ actually.
If I do on this one here,
So somewhere.
that's what
Oh no, don't worry about installing that because you have the compiler. So did you go to the C line website?
Yeah.
And downloaded the package? No, C line.
C9. I don't want to use that.
Doors
Don't
closed,
use
right?
that.
Sorry?
Oh,
Doors closed, right?
Yeah, the key.
Then I need to do
For new people or
You can
those who
use,
don't have license,
whatever ID you like.
we are using a Sea Lion software, and as a kindness of JetBrains, that the developer of the software, to our students we got licenses for 6 months. So normally license, if you go for the trial, it gives you 30 days. So you're very welcome to download it then. If you continue going to learn with us, send me an email, subject Sea Lion license, inside the body email, your name, your surname, email address, I can just copy and paste, and I will send you back a license for 6 months. So anybody needs it, send me an email. Email is basically on our website, admin@ctplondonuni.com.
Admin@ctplondonuni.com.
Or my normal address.
Maybe we should set up licenses at CPP.
Corporate.
I mean, I can just make distribution lists.
Yeah. Corporate licensing.
Okay, so
Anyway,
what would you
I
prefer
would
to use to?
Sorry?
I think I'm not
Yeah.
My name.
Well, basically, any of
I forgot
those
to write
that
my
you
full
use,
name.
So write it. Send again.
VS Code, I
It's
know,
no problem.
as a plugin will be able to detect it. So you don't have to worry about downloading it on the internet. You've got it installed.
So I don't need this.
You don't
But
need
this,
that.
but this one will be that specific ID. It won't be just the
Well,
other.
No, that's just the compiler. It's just the
then
command
again,
line.
compile
Just the
error
command line.
doesn't make sense.
What is going on?
Again, I just compile.
Okay.
Valid code is a vector.
So where is, show us where the class is. When did you instantiate your static? Yeah, you can't do that. It's English translation. You can't.
Why is that a static
Yeah,
array?
so one, I mean,
Because I wanted it available to all the different instances.
Okay, so you need to make an access.cpp and then include this header. Okay, fine. Oh, okay, cool. So go back to access.h.
It's not in there.
No, just cut that line out.
Why can't it be in line?
Because if you have more than one file, including the header, they will both treat it as a definition and create two places for it to live, obviously violating standard. That is fine. Now it's living one.
We did it like 2 months back. When the first 6 classes, I created, but yeah, there wasn't any image file just in one file.
That's fine, but static is special because it's a static piece of data. It has to the static.
I mean, because header in the implementation file will have that same thing again. So
Yeah, so everyone who includes it will then
copy
create space for it, and then you're going to duplicate it, which is legal. Okay.
I'm so slow.
Depends what kind of USB port it's got. If you're writing, where it's USB, obviously it's a little bit slower to write. It needs to read through it. Writing about 10 minutes. I generally prefer to
So that's why it's also,
and usually you may need it to, so it's a class, and like it's in class, it's going to give access to the front, it's opening it, right, you can have 3 buttons, so we refer to the caveat to it, right, is if you're going to have 2 different types, then it might be a bit inconvenient then because obviously the ordering but for the same time, which most of the time it should be right, you can do say operator less than.
Yeah.
Or we go so
So I want to make my own type, so I can go to that.
how many sessions have I got left on this topic? So 2 more.
The new module will be starting week after.
So today's the 15th, so I've got the 22nd and the 29th.
Yes.
Okay.
And we start on the 12th. So
Okay.
yeah, two more. 2 more. That's okay. 2 more.
It's quite fast. Thank you very much. This is yeah, 18 months ago.
I don't know if it's the internet. Generally, people think, yeah, once it's cached, once it gets cached in memory, then it should operate faster. Also, that's the first time that's been started, isn't it? Yeah, you're running a crash copy, so literally nothing's loaded. It's got to initialize everything. So once you've started it.
It's vector is fine.
It's a tool. Easier than C++. Easier than C++. Yes. Actually, it's not all that stuff.
When it has choice between
You use auto there, then it deduces it to auto the size return. Size.
I would expect it to
It's never ambiguous.
it's never going to be smaller than that.
It's going to be exactly what size return is.
Yeah, they with JavaScript.
But the question is, why does it why does it equal to some different answers?
Well, the principle exactly. Just the time to once. So it starts off like interpreting
I thought that the default
it comes to a
return
function that
becomes
is false and gets executed.
first of all sign.
It'll go and compile just that function. And execute three blocks.
Size determine so size is
JIT compilation.
And that's it in your browser.
So
size is just a function. Size is just a function this morning, and it's return type is size t.
So no, we want to know WebGL, but I assume that
the
it's
function actually returns
there's a sort of translation between JavaScript.
Because you can use auto, it's going to try.
That's a limited subset, desktop OpenGL, most commands you can translate it into desktop.
You can do really impressive stuff now. They never
Yeah,
worked out how it's done.
it's running on your local GPU.
Yeah,
Because the shader program will be downloaded to your GPU and compiled to
Yeah.
GPU.
Better if you want to use range-based
So WebGL performance isn't necessarily going to be terrible if you stay within the GL subset.
Yeah.
As soon as you step out the CPU back, things are going to be
Yeah, we have then there's no gain at that point. That's the point.
Sorry? Can I use this for you?
I was thinking about
So then you have to.
Yeah, I mean this is the way of doing it. It's not that it's incorrect. It's just that you're making the right part.
List.
Just do the same thing. Same thing.
Okay, well, so you can use the three element form. But leave it like that for a minute. You don't have to do this strictly. You can just do.
I'll reproduce what you're doing.
No, you can just do item. Okay. Oh, no, I'll tell you what. That's what I'm trying to do. Trying to modify it. Well, what you can also do is you can do. So I'm taking a constant. Taking all constants.
So you're allowed to do this. You haven't quite quantified it. So that's okay. To make it truly correct,
You don't have an instrument.
Yeah.
String has
sorry.
Well, if
But as an alternative,
yeah, if you want to do case and sensitive
find the
comparison,
elements.
that's a little bit more
So you can do
expensive. What you do is you go through each element. So you have your two strings.
Once you find
Look at the first element of each string.
you can then just
Convert them both to lowercase. Are they the same? If they're not the same, then these two strings are
then you have to
then you go to the next one. And so on and so on and so on. See at the end. If you reach the end of both strings, then there's
I ran my code, but it's not working.
Sorry, start one second.
no,
So you do say take this element here, it will then shift everything down. So because you don't care about the order, you know you can just copy one over here at the end. If you need to preserve the order, then
Okay, it is time for us to wrap up. Sorry, it's a little bit of a truncated session today. So who finished the exercise? Yeah, excellent. So your homework for next week is to do exercise 2 as well. Apologies to the people who already did that. I did actually have something really cool prepared to do this week, but hey, we didn't get to it, so we'll do that next week instead. But if you're particularly enthusiastic, it's already on GitHub, so you can go and find it. So yes, thank you everybody for coming. We hope to see you all next week when we'll continue from with what I wanted to go on and talk about today, which was algorithmic complexity and the standard algorithms. Yes, that's about it from me. So thank you everybody for coming, and please do come and join us for a beverage afterwards. Cheers.
Cool, thanks very much. Big thank you to Mimecast